Hello and welcome to today's lesson on half-life, which is part of the atomic structure in GCSE Combined Science Physics. So in today's lesson we're going to look at understanding what the half-life of a radioactive substance is. So if we've been successful and learnt in today's lesson, we should be able to understand and define what half-life is, look at the different factors that affect half-life and work out the half-life of a radioactive substance. So in today's lesson we're covering the following part of the AQA GCSE Combined Science specification: 6.4.2.3 half-lives and the random nature of radioactive decay. So when an unstable nucleus decays and becomes stable, the unstable nucleus can release radioactive emissions. But how do you measure the effect of this radioactive decay? Well, there are two steps to a nuclear decay. The first step is the nucleus decaying and becoming stable. The second step is the nucleus releasing radioactive emission. Now we can use either of these steps to measure the rate of nuclear decay. Now in step 1 we can measure the activity. Now the activity is how many radioactive nuclei decay and become stable every second. Now we measure activity in becquerels. Now 1 becquerel is 1 radioactive nucleus decaying and becoming stable every second. Now this was named after Henri Becquerel, who discovered the concept of radioactivity. Now from part 2 we can actually measure the count rate, which is the number of radioactive particles detected by a detector every single second. So we measure count rate in per second, and to get an accurate measure of count rate we need to ensure the detector is always the same distance away from a radioactive source. Now physicists use either measure depending on the ease of measurement, and it's not uncommon to see physicists use both measurements in an investigation. Now it's important to note that the activity and count rate can differ for a couple of reasons. Firstly, each decay might produce more than one emission, and secondly, the detector might not pick up all of the radioactive emissions given out, and finally, the radioactive emission might actually pass through the detector without being recognized. So you tend to find the count rate is always smaller than the activity. So let's just recap what we've learned. Radioactivity can be measured by two methods. Number 1, the activity, which is the number of radioactive nuclei decaying and becoming stable every second, which is measured in becquerels. The second way is with count rate, the number of radioactive emissions detected by a detector every second, and is measured in seconds to the -1. Now either quantity can be used to measure the radioactivity of a source. Now half-life can be measured by either the change in activity or the change in count rate of a source. Either unit can be used in physics. Now we measure radioactive decay by measuring either the activity or the count rate of a radioactive sample, and we do this to measure what we call the half-life of a substance. Now the half-life of a radioactive isotope is the average time it takes for either the number of radioactive nuclei of the isotope in the sample to half, or for the count rate or activity of your isotope in your sample to fall to half its initial level. So if a count is 600 counts per minute, the half-life is the time it takes to fall to 300 counts per minute, and that has to be the same time for it to fall from 300 to 150. Now all radioactive substances have a measured half-life. Now half-life is similar to rolling a dice. Now an unrolled dice could be considered like an unstable nucleus, and a rolled dice for one particular side, for example 6 or 2 or whatever, could be considered a stable nucleus. Now you can't say whether an individual dice when you roll it will roll a 6. So it's the same principle. You can't say whether an individual nucleus will decay. So this means radioactive decay is random. Now in addition to this, you can't influence whether an individual dice will roll a particular number like a 6. And the same principle, you can't influence whether an individual nucleus can decay. So we say radioactive decay is a spontaneous process. Now you can predict how many dice would roll a 6 on average, so by that similar token you can predict how long it would take for half of the unstable nuclei to become stable. So this principle is called the half-life of a substance. Now, the half-life for a particular radioactive isotope is always constant, but we always state that the half-life is the average time because radioactive decay is a random event. So the half-life is the average time it takes for the mass of the radioactive isotope to drop to half its original mass, the count rate of the radioactive isotope in a sample to fall to half its initial value, or for the activity of the radioisotope in a sample to fall to half its initial value. Now, the radioactive decay is constant as each radioactive nucleus has the same chance of decaying as each other. So the random nature of radioactive decay requires repeat readings to be made over a long period of time, as this will minimize any random error you get in your investigation. So for substances, we can measure how many radioactive nuclei they are, and over time the radioactive nuclei become non-radioactive, and so we can therefore work out the time it takes for the radioactive count rate or the number of radioactive nuclei in a sample to half, and it should remain constant. So it doesn't matter if you go from 600 to 300, 300 to 150, 150 to 75, 2 to 1, it always takes the same time for a radioactive isotope to half in its value. Now just remember, when a substance becomes, when it decays, it doesn't disappear out the universe, rather it's becoming non-radioactive. So over time, more non-radioactive or stable nuclei are produced. Now more are produced at the start of the process and fewer are produced over time, and we call this process exponential decay. So, for a substance, we can measure how the half-life takes place for each one. Now, let's consider a proportion of a sample which is radioactive. Now, because radioactive decay is a random and spontaneous event, this means individual behavior cannot be predicted, it cannot be influenced, so therefore the chance of a decay happening to a nucleus is the same each time. So this means it takes the same time for a radioactive sample to half, no matter what the value of the sample is. So this leads to the concept of the half-life. So the time it takes to go from 1 to a half, half to a quarter to an eighth to a 16, and so on and so on and so on, is always the same value. And the reason why this is because all nuclei have the same chance of decaying. So it always takes the same amount of time for half of those nuclei to decay and become stable. Now you can work out how many half-lives have taken place by taking the original value you have, halving it until you reach the wanted value, then working out how many times you've halved it. So for example, if we wanted to work out how many half-lives have taken to go from 1 of a sample to a 16th of a sample, you halve 1 until you get to 1/16 and work out how many times you've halved it. So in this example, it's been 1, 2, 3, 4 halvings to go from 1 to 1/16, so therefore it's been 4 half-lives. At this point, you can then find out the time taken to go from 1 to 1/16, or whatever your particular question asks you, by multiplying the number of half-lives by the time it takes for one half-life. Now you can actually fully work out the change in mass or the change in nuclei every half-life and then determine the values, but there's actually quite a long and time-consuming method. So instead we can use a more mathematical method. So if we look at the following example here, we can see that there's actually a pattern that develops that we can calculate a general formula to work out the mass remaining after a certain number of half-lives. And it's the following idea. So we can determine the mass of a radioactive isotope left after radioactive decay from half-life via the following formula. The mass of the radioactive nuclei remaining is equal to 0.5 to the power of the number of half-lives passed times by the initial mass. Or you can also write it out as the initial mass divided by 2 to the power of the number of half-lives. Now this is the same equation written in different forms because a half, so dividing by 2 is the same as timesing by a half. Now we can use other radioactive values such as activity and count rate. So for example, this formula can be adapted to work out the mass, the activity, or the count rate due to nuclear decay easily. Now, this is a formula you've got to remember for your examination. So you could say, what is the count rate of the radioactive nuclei remaining? Well, it's C over 2 to the power of n, where C is the initial count rate. What is the activity remaining after n half-lives? Well, it's the initial half-life divided by 2 to the power of the number of half-lives. So let's look at a particular example of a question. So a particular radioactive isotope has a half-life of 6 hours. A sample of this isotope contains 60,000 radioactive nuclei. Calculate the number of radioactive nuclei that of the isotope remaining after 24 hours. So what we say is, well, n equals 4 because in 24 hours there's going to be 4 half-lives, because one half-life is 6 hours and there's 4 lots of 6 in 24. So therefore the number of radioactive nuclei is the initial value, which is 60,000, divided by 2 to the power of the half-lives. 2 to the power of 4. Now 2 to the power of 4, which if you put into your calculator and work it out, is 16. So therefore it's 60,000 over 16, so it's 3,750. Now the activity, count rate, radioactive nuclei can be plotted against the time, and we get the following graph. Now this graph occurs as the nuclei radioactively decay over time and become stable. So the number of radioactive nuclei, the count rate, or the activity all falls with respect to time. Now this graph is an example of an exponential relationship. Now an exponential relationship is a relationship where the rate of change is constant as a percentage of the value. So in radioactive decay it's an exponential relationship because the time taken to fall by 50%, the half-life, is constant. Now we know that this is an exponential decay because the exponential decays because the rate of change is a decrease. The actual amount of radioactive nuclei decaying is slowing down. Now we can actually work out the half-life of a substance via graphical methods. So to do this, you plot the activity or the mass of radioactive nuclei or the count rate on the y-axis and the time on the x-axis. Now radioactive decay will always form the following exponential decay curve. Now what you've got to do to work out the half-life is draw two lines on the graph where the activity is half of the other. So for example, one line could be at 200, the other line could be at 100. One line could be at 400, the other one at 200. One line could be at 6, the other line could be at 3. One line could be at 100, the other line could be at 50. So you find two values where one is half the other. You then extrapolate the lines downwards to the x-axis. You find the time for each value. You then find the difference between those two times, and that is the half-life. So let's have a look at an example. So in this case, I'm going to choose an activity. So I'm going to choose 8,000. So I then go to 8,000, go across the line, go down to the time value and work it through. I then do the same for half of the value of 8,000, which is 4,000, and therefore I can work out the time at 4,000. The half-life is therefore the time between those two values. So the half-life is the time taken between the first activity measured and the second activity measured. Now again, you can do this for the mass of a radioactive isotope, the count rate, or the activity. Now always try to use rounded numbers, as it's easier to derive these values because it's easier to measure. Now let's have a look at an example. So in this case, 8,000 going down, we work out to be 2.5 on the scale. 4,000 going across and down, we work out to be 9.5 on this particular scale. So 9.5 minus 2.5 equals 7 seconds. So our half-life is 7 seconds. Now it's actually best practice to do this for a number of different values. So maybe do 6,000, 3,000, 4,000, 2,000, 10,000, 5,000, and calculate a mean, because doing repeats and calculating a mean minimises the random nature of radioactive decay. Now finally, whilst measurements show that the mass decreases exponentially, it decreases by a constant factor, 50%, in equal intervals of time, which is the same for the count rate or the activity, the radioactive decay curve never falls to zero. Now in practice, the level of radiation will fall to a level indistinguishable to the background radiation. Now if you carry this out for multiple different values, so you do 1 and 0.5 You do 0.5 and 0.25, 0.25 and 0.125, 0.125 and 0.0625. You should try and calculate the value for each one. Now, in theory, the half-life remains fixed for any two values that you pick. So the value calculated for half-life should be the same no matter what two values are used in this measurement. Now, in reality, the half-life varies slightly because radioactive decay is a random event. It's like saying if you roll a dice, you're not going to get 1, 2, 3, 4, 5 and 6 on all the 6 goes. Sometimes you might get 3 6s in a go, you might get 2 4s in a go, and not have 5 for like 7 rolls. So as a result, you will get a slight variation because radioactive decay is a random event. So like mentioned before, it's best practice to take multiple half-lives and find an average. Now, the half-life for a radioactive substance can be worked out from a graph in an experiment. So you can plot activity or mass or count rate against time, and then you must draw on the graph 2 lines where the activity is half of each other. You then plot the lines downwards and find the corresponding time, and the difference in the time is the half-life. So radioactive decay is a random process. The half-life of a radioactive isotope is the time it takes for the number of nuclei of the isotope in a sample to half, or the time it takes for the count rate or activity from a sample containing the isotope to fall to half its initial level. You should be able to explain the concept of half-life and how it's related to the random nature of radioactive decay, and determine the half-life of a radioactive isotope from given information. And you should also be able to calculate the net decline expressed as a ratio in a radioactive emission after a given number of half-lives. So if we've been successful and learnt in today's lesson, we should be able to understand and define what half-life is, look at the factors that affect half-life, and finally work out the half-life of a radioactive substance. So I hope you've enjoyed today's lesson. We'll look at half-life in the topic of atomic structure in GCSE Combined Science. Thank you very much for listening and have a lovely day.